Hello everyone. In this video, we are going to study about UV visible spectroscopy. So let's get started. Very first, what do you mean by spectroscopy? The spectroscopy is the scientific study of interaction between a matter and electromagnetic radiation, which means as light. So spectroscopy involves the measurement of amount of light or electromagnetic radiation which is absorbed, emitted, or scattered by a sample or chemical compound as a function of the light's wavelength or frequency. Because different atoms, molecules, and chemical bonds absorb or emit light at very specific unique wavelength, which we can call it as the fingerprint wavelength. The scientists can use spectroscopy to identify the composition, structure, and physical properties of the chemical substances. So how it works? So every substance or a chemical compound has its unique chemical and energy structure. So when that molecular chemical compound exposed to electromagnetic radiation, it absorbs the energy and jumps from the lower energy state to higher energy state. And because of these energy jumps are specific to the structure of that chemical substances, the light it interacts with tells the story about what the substance is made of. So there are three possible interactions between a matter, that is an atom, molecule, or compound, with the electromagnetic radiation. So in that, the first one is absorption, second is emission, and third one is scattering. So the very first is absorption. So simply, in absorption, the electromagnetic radiation interacts with an atom, and in that atom the electron which is present at the lower energy state absorb the energy from the incident electromagnetic radiation and get promoted to the higher energy state orbital. This phenomenon is called as absorption. In the second interaction, which is known as emission, when the electron at the higher energy state orbital returns to the original low energy state orbital, it releases certain kind of energy in the form of electromagnetic radiation. That phenomena is known as emission. And the third interaction is scattering. When the incident electromagnetic radiation interact with the atomic structure of the matter, it get redirected into various directions, and that phenomenon is nothing but the scattering. So these are the three interactions of electromagnetic radiation with matter. So what do you mean by electromagnetic radiation? So an electromagnetic radiation is the form of energy that behave both as wave and the particles in the form of photons, and it travels through space. Unlike sound, which require a medium, that is air or water, to travel, the electromagnetic radiation can propagate through vacuum at the speed of light. And the electromagnetic radiation EMR is composed of two fields, an oscillating electric field and an oscillating magnetic field, which are perpendicular to each other and to the direction of wave travels. So there are few core properties of electromagnetic radiation, including wavelength, frequency, speed of light, and energy. So this can simply be understood in the next schematic. So you can see here the particular structure of a electromagnetic wave or electromagnetic radiation is there. So the curve which is going upside is known as the crust, and the curve which is going downside it is known as trough. and the distance between two successive crusts or two successive troughs or between one crust and one trough, that distance is known as wavelength and denoted as lambda. And the maximum displacement from the equilibrium is known as amplitude, the wave's amplitude, that is C. The second property of the wave is frequency, denoted by nu. The number of full waves passing through a fixed point per second is known as its frequency. So if low number of waves passing through a fixed point per second, we can call it as low frequency wave, and vice versa. When the high number of waves are passing through a fixed point within a second, we can call it as a high frequency wave. Next is energy. So what is the relationship between energy, the frequency, and the wavelength? So c, that is speed of light, is equals to lambda nu. C, that is speed of light, which is 3 into 10 raised to 8 meters per second, as we know, that equals lambda into nu, and energy E is equal to h nu, where h is the Planck's constant. And when we put the value of nu, that is frequency, here as c by lambda, we will get E is equals to h c by lambda. And here is the relationship between energy, frequency, and wavelength. So energy is directly proportional to the frequency of the wave, and energy is inversely proportional to the wavelength. So as frequency increases, the energy increases and wavelength decreases. And as frequency decreases, the energy is also decreases, and wavelength means the wavelength is higher. So again, the high frequency wave have high energy, and the low frequency and high wavelength containing wave or electromagnetic radiation is ultimately the low energy wave or electromagnetic radiation. So next is the electromagnetic spectrum. So electromagnetic spectrum containing different types of electromagnetic radiations according to its wavelength and its frequency. So in this particular diagram, you can see from right to left there is decrease in the wavelength, and from left to right there is increment in the frequency. So here the rightmost electromagnetic radiation type, that is gamma rays, it is having highest energy because it has highest frequency. So highest frequency, highest energy, and shortest wavelength containing is the gamma rays. And in the leftmost side you can see the radio waves, which are having lowest energy as they have lowest frequency and longest wavelength, or we can say highest wavelength. And in between you can see multiple other radiations also. So you can see here the X-rays, they are having low frequency and high wavelength as compared to gamma rays. Next is UV visible rays, which are having low frequency and high wavelength as compared to X-rays and gamma rays. Similarly, the IR rays, infrared rays, they are having less frequency and high wavelength as compared to UV visible and X-ray and gamma rays. Similarly, microwaves having low frequency, high wavelength as compared to IR and UV visible rays. And finally, the radio waves, they are having the longest wavelength and lowest frequency and energy. So you can learn this electromagnetic spectrum. And the important thing is its dimensions. Means you can see here there is 10 raised to minus 12 meters in case of gamma rays, and here 10 raised to 3 meters in case of radio waves. And in case of UV visible range, it ranges from 10 raised to minus 8 meters to 10 raised to minus 5 meters, means around 10 nanometers to 800 nanometers. Next is introduction to the UV visible region. The UV and visible regions of electromagnetic spectrum represent the range of radiation that interacts with the electronic structure of atoms and molecules, and that range it is utilized by UV visible spectroscopy, which is a widely used analytical technique in laboratories worldwide. So this UV visible region, it is bridges the gap between high energy X-rays and low energy I rays. So you can see here, so it is the UV visible region which is lies between the high energy X-rays and the low energy IR radiation. So the UV region lies between 10 to 400 nanometer, and visible region lies between 400 to 750 nanometer. So in some sources you can find 800 nanometer. So it is generally 400 to 800 nanometer. So UV region is subdivided into vacuum UV, far UV, and near UV. So vacuum UV lies between 10 to 200 nanometers, far UV 200 to 300 nanometers, and near UV 300 to 400 nanometers. The next point is the UV visible spectroscopy introduction. So the UV visible spectroscopy or ultraviolet visible spectroscopy is an analytical technique used to measure how much chemical substance absorbs the light in the UV visible region of electromagnetic spectrum. So it is one of the most common tool in chemistry and biology discipline to identify the compounds, measuring their concentration and studying their molecular structures. So the basic principle behind UV visible spectroscopy is electronic transition. So what is the electronic transition? So there are few points to be considered to understand the electronic transition includes energy absorption, then promotion, and molecular fingerprint. So first one is energy absorption. So in an electronic transition, when the molecule is exposed to UV visible light, the electrons in the ground state absorb the energy from the incoming photons or incoming electromagnetic radiation. That means the UV or visible radiation. The second thing is promotion. This absorption makes that lower energy state electrons to jump from their ground state, that is a low energy orbital, to an excited state or a higher energy orbital. This is known as promotion, or jumping from low energy state to high energy state. And third is molecular fingerprint. So a specific amount of energy or wavelength is required to make this promotion or jump, which is depend on the structure of molecule, and hence the because every molecule has its unique structure, it is also having unique absorption spectrum, and hence it is called as a molecular fingerprint. So next, let's get deeper to the electronic transitions. So there are a few types of electronic transitions. So in UV spectroscopy, the electronic transitions occurs when an electron absorbs the photon energy and moves from low energy orbital to high energy orbital. So the low energy orbital is filled and the high energy orbital is empty or unfilled, and it is also known as anti-bonding orbital. Okay, so the classification of transition is as sigma to sigma star transition, then n to sigma star transition, pi to pi star transition, and n to pi star transition. So these four are the most common transitions in UV visible spectroscopy. So in this energy diagram, you can see here, this is sigma, which is a filled low energy sigma orbital. This is pi. Pi is the filled low energy pi orbital. Then next is n. The n is non-bonding electron charge. So n is non-bonding orbital. And pi star is unfilled or empty high energy anti-bonding pi star orbital. And next the sigma star, that is the empty or unfilled high energy antibonding sigma orbital. So the low energy orbitals, the electrons from the low energy orbitals jump to the high energy orbitals, and this transition occurs. So the very first transition is sigma to sigma star transition, where the bonding sigma electrons absorb the UV energy and promoted to antibonding sigma star orbital, and it is occur in vacuum UV region below 200 nanometer, and it is most common in the saturated hydrocarbons or saturated compounds containing single covalent bonds such as alkenes, example methane, ethane, propane, etc. The second is the N2 sigma star transition. Second is the N2 sigma star transition where non-bonding electrons get promoted to sigma star, that is high energy anti-bonding sigma star orbital. It is occurs again in the saturated compounds which are containing heteroatoms such as oxygen, nitrogen, halogens, etc. Where the non-bonding n electrons, lone pair n electrons promoted to the sigma star, that is anti-bonding high energy sigma orbital, and it is occurs in saturated compounds with heteroatoms such as water, alcohol, and amines, and it is occurs in the range of 150 to 250 nanometers. The third transition is pi to pi star transition. This is the pi to pi star transition where the bonding pi electrons promoted to antibonding pi high energy antibonding pi star orbital. So it is occur in 200 to 400 nanometer range, and it is occurs in the unsaturated compounds containing double or triple bonds such as alkenes, alkynes, carbonyl groups, etc. And the fourth one is the N2 pi star transition where the non-bonding n electrons, the non-bonding lone pair of electrons promoted to the anti-bonding pi star orbital, high energy anti-bonding pi orbital, and it is occurs in again unsaturated compounds containing double or triple bond and containing a heteroatom such as oxygen and nitrogen, examples carbonyl group C double bond O, then nitro groups such as NO2, etc. And it is occurs in the range of greater than 200 nanometers. So you can see in this energy diagram that is the sigma to sigma star transition require the highest energy, and the N to pi star transition occurs having the lowest energy than others. So in next video we are going to see the relation between the absorbance and concentration, which is given by Beer and Lambert's law. Its derivation, deviation, and limitation. So stay tuned for that video. Like, share, and subscribe. Thank you.